coasters and swinging buckets. Have you ever been on an upside-down roller coaster and wondered why the roller coaster car didn't fall off the track? It turns out the same properties of circular motion are responsible for your safety on a roller coaster. This roller coaster is different than a car going over a hill, since you can see the track is pushing down on the roller coaster car at the top of the circle, while the road pushes up on a car. Also, while we can think of the roller coaster car as being in uniform circular motion at the top and bottom of its circular path, it is not in uniform circular motion along the sides of its circular path. It speeds up as it falls, which makes it so exciting to ride, so its speed is not constant, but it has an approximately constant speed at the top and at the bottom, so is in uniform circular motion there. But those speeds are not the same. It moves faster at the bottom than at the top. The same diagram we used earlier works for a roller coaster car. The difference is that the normal force from the track is always pushing towards the center of the circular path, so there is no maximum speed at which the car will fly off the track at the top. But there is a minimum speed for the car to stay on the track. We'll find that minimum speed in the next few slides. There are numerous other safety features that keep a real roller coaster car on the track. For this problem, we'll assume it's a test without those features. At the top of the circle, the normal force and weight both point in the same direction as the acceleration. That's because the normal force of the track on the car pushes downwards towards the center of the circle. Using our free body diagram, we can write an equation for the car using Newton's second law and solve for the normal force. So we have two forces, mg and the normal force. Both are pointing in the negative direction, down. So we have negative normal force minus the weight mg equals negative ma, since a is also pointing down. So we can just multiply this whole thing by -1 so that these all become positive. So now we've gotten rid of those negative signs. And we solve for the normal force, so we subtract mg from both sides. We can factor out that m, and we can replace acceleration with v squared over r since we're in circular motion. And here's our equation for normal force. And you can see that as v squared increases, so does the normal force. These are directly proportional. There is no upper limit to the speed. The normal force will just get larger as v increases, as long as the track is strong enough to supply that normal force. But is there a lower limit? To determine that, keep in mind that the normal force is the push of a surface on an object. That push can be reduced to 0, but can't be less than 0. That would make it a pull, not a push, which is something the normal force cannot do. So the smallest value for the normal force in the above equation is 0. When the normal force equals 0, the car and its passengers are quote-unquote weightless, since there is no surface pushing on them. Let's find the velocity at this moment when the normal force equals 0. So we plug in 0 here, and so we have two pieces multiplied together. We don't really care where mass is 0, because that won't tell us anything about this velocity. So let's see what happens when this piece becomes 0. So we set this equal to 0, and we add g to both sides. We multiply both sides by r. We take the square root of both sides, and we get velocity equals the square root of g times r. At this velocity, the car and its passengers become weightless. The track won't be pushing down at all in this moment, at this velocity. So what happens at even slower velocities? On the prior slide, we solved for velocity when the normal force equals 0. We also discussed earlier that the normal force cannot be reduced below 0, since it would become a pull rather than a push. So the normal force equals 0 for velocities that are less than or equal to the square root of gr. So we can use our interim result from the prior slide, v squared equals gr, and we can instead solve for r. This gives the radius of circular motion whenever the velocity is less than or equal to the square root of gr. So this is our equation for the radius. So when the velocity equals the square root of gr, the car will stay on the track but become weightless. What happens to r when the velocity goes below the square root of gr? The car is no longer in contact with the track since the normal force equals 0. Since g is a constant, then as v squared gets smaller, so does the radius of the circular motion of the car. The roller coaster car will follow a circular path that is below that of the track. It will fall away from the track, so it'll follow the blue path instead of the red path. For the same reason that an upside-down roller coaster won't fall off the track, water won't fall out of an upside-down bucket if it's moving in circular motion at a fast enough velocity. The free body diagram and equations are identical, so the minimum velocity is also the same. Like the roller coaster, the bucket speeds up as it falls down the side of its circular path, so it is not in uniform circular motion except at the top and bottom, and its speed is faster at the bottom than at the top. Safe speeds are when the normal force is greater than or equal to 0. That will be when the expression in the parentheses is greater than or equal to 0. So we take this piece here, set it equal to 0, or greater than or equal to 0, and solve for velocity, and we see that as long as the bucket has a velocity of the square root of g times r, or greater, the water will stay in the bucket, even when it is upside down.